Welcome to this video on digital electronics. We will cover a more general approach to circuit design by using Karnaugh Maps. We will also see how this makes designing complex circuits an easier process and allow us to produce the simplest circuit, made from the least number of gates. Let's begin with the familiar territory of truth tables. Karnaugh Maps are used to make circuit design simpler, once we have the behavior that a circuit needs to represent. This truth table is more complex as it is more difficult to determine the final circuit, unlike with the example from the last video. This is where Karnaugh Maps are useful. Here, we can see how we have the two sides of the map labeled as A and B, with the possible values as 0 and 1 shown for each cell. The color coding shows how when the output is a 1, we put a 1 in the corresponding cell. Now we need to consider what this means. We use Karnaugh Maps to analyze bit changes, one at a time. How the output changes as we change each bit in the inputs tells us whether each variable is important in making the output a 1. By bit changes, we mean B changes between 0 and 1 when we go vertically, and A changes between 0 and 1 when we move horizontally. As such, we can use looping of 1s to show when the output is true. It is important that we are only considering a single bit change at a time, so we can link changes in the output to variable changes to identify how variables influence the output. So we can never loop diagonally, but we can loop around the edges of the map. Here we can see from the first loop that a bit change in A does not change the output, so the behavior for these outputs is determined by when B is 0. So we obtain an output of 1 by inverting B with a NOT gate, hence output equals NOT B. With similar reasoning for the second loop, we see that the other true outputs come from when A is a 1. Notice that overlapping of loops is acceptable, but we have to ensure that all instances of the output being true are accounted for. So, to piece this all together, we can see that the output is true when we have not B or when we have A. Hence, we combine these by using an OR gate, which is denoted in the Boolean expression by the plus sign. So now we can draw the simplest solution to represent this behavior. But it is worth mentioning that other more complex solutions can also be correct, but it can cause problems when implemented in reality. We conclude with some final remarks. This video has covered how more complex circuit behaviors can be realized with a circuit using as few gates as possible to give the simplest solution. Like and subscribe for more.